Well, let's try and get started and let's see how that goes. So welcome to our first demo day. It's always my favorite part of the semester where you are demoing and I'm just kind of listening here and providing, feedback. As I know some of you are a little tired, working late into the night, and I understand that. Let me just try to remind the whole class as to what the point of MP0 was. The design you were doing in and of itself wasn't necessarily the fundamental goal of that assignment. It was supposed to be a fun, somewhat challenging design that you had to implement. But my goals for that were, first off, giving you some additional familiarity or getting you your first familiarity with using the FPGA design tools, as well as all the other assorted infrastructure for this class. And we're not quite right there yet. MP1, there's going to be some more of that happening. But that's my first goal. So if you got that, if you feel like you have something of a bead on what Vivado is all about, you've succeeded in MP0. The second goal was to see how your teams are doing. The somewhat random, somewhat arbitrary teams we put together to start the semester. Did you feel like a team? Was everybody contributing to some amount? Did everyone feel like they had some roles? There is less ways to partition the work in MP0 than there will be for all the other upcoming labs. So I understand that part's hard, but I'd like you as a team to reflect upon that as well. What were we a functioning team? The labs are going to get a little bit trickier in some sense than this MP0 lab was. So do we have a functioning team? So ultimately, whether you got the design working and it's amazing and super fast, or whether you struggled and you never quite got it working, that's okay. That certainly for this assignment, it was good to try. If you learned some things along the way, you've succeeded. Um, but it's if you felt you had a team and you felt that you were there for each other and splitting up the work as best you could, and you felt better than the individual pieces as you came together as a team here. Um, that's an important thing because you're going to need that this semester. All that having been said, we're on a pretty tight timeline here. I'm going to try to hold everyone to 10 minutes, and if you use fewer minutes, that's fine. If you use more, I really do want to hear from you. So I think you'll see, just looking at these slides, that the designs are quite similar. Even the parts that are different, they all kind of smell very similar in terms of what you're trying to do, because the design was pretty bespoke in terms of, here's what you have to implement. You can't do too many tricks along the way. What was really different in how you use the tools, and how you took advantage of the resources available on the FPGA. And that's kind of fun to see. So I'm looking forward to seeing really 8 different approaches ultimately in terms of how you implemented this. And if you see some tips and tricks, it could be worthwhile for you to write those down, because some of the things that were learned in this assignment, I think will also pay dividends for future assignments. So having said that, in just a second here, I will mute myself, and group 4, we can do this however we want. If just one person wants to speak, that's fine. I see basically everyone's here, so I'm not worried about participation or anything like that for this demo. Everyone has succeeded for that 5 points or whatever it is for the assignment. But just walk through as you see fit, and we can do Q&A at the end. But also, if people want to type in questions in the chat, I could bring those up, and we can have that discussion within that time frame of 10 minutes here. So group 4, kind of randomly chosen. Don't take it personally. It looked like you had a good presentation, so I thought let's start with yours, and you can get started.
Okay, so I think we took a pretty basic approach to this. We pretty much just, you'll see in this diagram, we've got that big DMEM that we were given. We've got the A matrix that we were given. And then you'll see down below that, we have a little math 4-channel module. Basically, all that does is that operation that was in the PDF that just multiplies the vectors and then adds them together. We have 8 of those. So to accommodate that, we had to have 16 ports on our DMEM, which took quite a bit of time to synthesize, we're thinking. And then, I'll let someone else take over, because that's about all I have to say. That's our design there.
So also for the state machine, we made it so it takes a decent amount of steps. So first off, it has the steps of resetting everything, and then it goes and grabs the A matrix first, all at once with the 16 ports, along with some of the vector values, because 16 ports was more than enough just to get the A matrix. So, and then after that, we just loop through in the next state to get all of the X vectors. And then once we count up enough to end up getting close to 10,000, since we added in some pipelines afterwards, it wasn't exactly, so the state wasn't done the same time that the final values were done. So then after that, finish, grab the last X vectors, and then we end up setting the done signal at the last state for the state machine. And then here, I believe what we did here was, I can't remember exactly, but this is when we doubled the amount of ports we got, I think. We didn't end up decreasing the clock cycle because it ended up getting too close to the due date, and it was synthesizing for like 2 or 3 hours for some reason and just wasn't finishing. So we ended up not being able to do that. This is still with the 100 megahertz, 10 nanosecond clock cycle time. Wish we could have gotten it down. We think we could have decreased it close to half, but not exactly half. So it kind of sucks that we didn't get that down. But I didn't do this part, so I don't know the 0x0 part as well. If somebody
Yeah,
else wants to
so
explain that.
one of the issues we ran into was SY total. We just flipped our vectors a little bit. AJ and I had discussed, and we assumed that it didn't really matter what order, but apparently it does. And then we had simplifying our DMEM. And AJ, did you simplify the DMEM?
It was kind of, I guess, me who started it, but I think it was Ben who ended up finishing simplifying it.
Yeah, so I guess the simplification of DMEM, we basically just, everything is inside one process statement with one clock. We have one address port, and then we just add to that inside DMEM. So DMEM is really just 16 lines of output 1 equals address, output 2 equals address plus 1, and so on. There's nothing at all else going on inside there.
But yeah, that allows us to read a whole bunch at the same time, which has allowed us to keep our pipelines kind of fed while we were calculating it. And we also, when we were doubling the amount of pipeline, or I guess concurrent processes that we had to rewrite most of our code to use for loops to generate the components rather than just kind of copying and pasting code. So that was kind of a bit of a learning curve, especially for me, since I haven't done a whole lot of hardware design before. So
another big thing that we ended up doing that we didn't really like was that we had to do our math by hand in order to verify the waveforms section there. We were getting all the right outputs all the way through our waveform, except our final total was wrong. So that's where we had to sit there and look at that and do the math by hand, and we got pretty good at Excel. Another big problem we talked about in the Discord, was that our UART was just outputting all threes. The solution to that ended up just being we'd auto-formatted all of the source code, so it was a little easier to look at, and it all was exactly the same across all of our devices. For some reason, that broke UART, so fixing that, we just reverted back and that fixed it. That's all we have for a presentation. So does anyone have any questions they want to ask? Or
I was actually gonna ask the rest of the classes as well. I mean, just something to think about. So you mentioned, it was kind of awful. We had to go to pencil and paper and kind of trace through the math. I think you're gonna have to be doing that a lot this semester, right? When everything works, you don't have to do it. The final result looks great. You just see things in model sim or the simulator, and everything is correct and on the board as well. It's pretty common, and so you'll see that in a lot of our pre-labs as well. MP1 isn't so bad, but the MP2 pre-lab is going to look like a lot of paper and pencil busy work. It's not busy work. As you're actually debugging these designs, and when becomes a decent amount of math, I don't think there's any real way to find that bug if you don't have the pencil and paper math kind of worked out to see, oh, yeah, that's exactly where things got swapped and things are kind of not right. Other questions from the class? So there's a question about for loops. Yeah, so there's both generate loops, which you may recall from a 381 class that you can synthesize those. Those are just copy paste blocks. You can also synthesize for loops, right? It's really just do the same thing multiple times. They don't synthesize like a for loop would in that it's doing anything sequentially. It's just a way of simplifying lines of code. So both are valid. Maybe you heard, depending on who you took 381 with, that for loops are bad. There's really nothing of the sort that's the case, right? It's what is the model of my hardware, and does this code infer that hardware that I want back out? So in that perspective, if you have a complicated multi-dimensional signal to make the pencil and paper math a little bit more feasible, then having things like for loops inside a process block are perfectly fine. You just don't want to treat it like, first I do the first iteration, then I do the second iteration, then I do the third iteration. That's more modeling software than what we want to model in our hardware. So it's valid. In either case, it's totally valid. Other questions for group 4? So were you successful? I mean, okay, I define success to start things off as team was working well and you worked hard on it and you learned a lot about the tools. These are not the correct results. Did you eventually get the correct results or something close to it by the end?
We were having issues where when we ran the C code on everyone's computers, we were getting different vectors, even though we were seeding random. So that is what we were getting from the C code with this set of vectors.
That's weird, but okay, fair enough. So if that's what you're getting with the C code and that's what you're getting from the hardware, then we'll call that good. I mean, if it's consistent, that should be sufficient, I would think.
It's possible that is just because I'm using MSys for Windows and I didn't compile it on the same Linux box. So it's probably just an implementation thing, but we just use the same BRAM file for everyone. So, or DMEM for whatever file it was.
Okay, so it's possible that given the same DMEM file or given a different DMEM file, you'd get consistent results, I would think.
Yes, yeah, they are consistent. So.
And the other thing I wanted to add, and this is something that it's not like I covered it in class, and it's not like you would have seen it in different classes. And then you were talking about, a 16-port DMEM, right? We were trying to, although different groups figure this out in different ways, we were trying to infer blockgrams on that device. That the FPGA chips that we use, and specifically the ones for this semester, have these physically instantiated memories on the chip that we want to take advantage of. They're relatively fast. They can store a decent amount of data. Those physically have 2 ports on them. So when you want to make a design that has a 4-port memory, the tools aren't going to be able to map it to those physical chips on the device. Other teams saw that when they were trying to map a very wide memory, which in theory should work, but in practice for some, it wasn't working. Those who had designs that had 40,000 and 50,000 lookup tables, that's probably how it was implementing your DMEM. Which wasn't my intention. It wasn't my intention. And that's where we're also starting to see the really long synthesis times. None of these synthesis times for this assignment were supposed to be more than 5-10 minutes max. So different teams solved that different ways. And it looks like your team came up with a solution that also worked for that. Thanks, team. Let's move on to team number 5 with some fancy animations.
Yeah, so hi everyone, we're team number 5. For approaching our design, we went with just basically get it working, not get it working and get as fast as we can. So with that in mind, this was our design. It is a simple 6-state machine that each of the states that performs their own little thing, with 4 of them being used for everything. So we started in it that just gets everything going. Read A, we iterate through to get all of our 4x4 arrays. Once we get all the A arrays, we go down to read X, which then gets 1 X matrices that gets sent to a matrix multiplication module, which needs a buffer. So that's why we have that matrix mult. And then once it goes there, we have to add it to the other ones. And then in there, we have a counter. If it gets up to 10, if it's not 10,000, it goes back to read X to get another X matrix. Otherwise, it is done. As you can tell, not the most efficient design, but our goal was just simply to get it implemented because we had some errors.
Yeah, and along the way, we did run into just a few minor bugs and issues.
The first of which was when we initially were trying to read in from the data memory, we were finding that between the stages, it would skip the second read-in value because we would increment the memory address that was being read from too early. So our solution to that was to offset the memory read addresses between our stages to one address less so that it would read in properly. Another bug we had that took a bit more time to figure out was our Vivado was flat out crashing. No warning boxes came up or anything when we tried to simulate our initial design. We didn't really figure out exactly what the issue was, but we think it's part of the project because when we copied the project to one of our personal drives and tried simulating the project on a lab computer, it worked. And then when we copied the project back over into our main shared folder, it continued working.
Yeah. Here's our results. Nothing too fancy. As you can see, the time isn't the best, but we did get correct results.
I'm going to jump in here again briefly. So it's another group where I guess maybe something's weird with that C code I provided. It's old code that's not like using any modern approaches. I was expecting, the idea was that everyone have the same exact vectors in the end. So if your software matches your hardware, that is success. You've just given me a lot more work now that if I want to go through and actually verify that your stuff is correct, I have to actually run synthesis and check it on. But Matt, it shouldn't matter. That's part of a standard for seeding a random number generator. It shouldn't depend. I guess I'm surprised it does. So at some point in the last few years, functionality for seeding a random number has changed, which it shouldn't. Okay, well, that's lesson learned for me, and that's good to know, I guess. So I'm glad. I'm glad that I thought some teams didn't have it working. It's clear that you have it working, so that's wonderful. You can continue.
All right.
Sorry for interrupting.
Yeah, so for essentially summary of what our decision-making process is, we went with a pretty basic design, and we were going to look at some optimizations, but we basically, those bugs that we talked about in the previous slides kind of took up a lot of time, and when we were looking at how we were going to optimize stuff, we didn't really feel comfortable trying to read a bunch of the file at once, and we thought that was going to be too big of a data flow restriction to actually speed it up enough to actually be competitive. So we called it good. If anyone has any questions.
Any questions for Group 5? I'm still a little flummoxed by my misunderstanding of standard library random functions. So this is the elaborate view of your design, and I think a lot of teams are seeing that can be a pretty useful view. It doesn't really tell you how ultimately the design gets synthesized at all, because this is pre-synthesis, but it gives you an understanding of what the tools think the structure of your design is. So I think that can be a very useful view, and certainly as you're looking at other code bases that aren't your own, seeing how things are actually wired together. So that's a useful thing. I would also add for Team 5. Your implementation that you were downplaying, saying, well, this isn't super great. That's exactly what I was hoping for. So that's a perfectly valid, wonderful, 100% design that you did this week. It's for teams who got that done early. That was my hope for you. If you got that done early, and frankly, if your other classes were boring or you didn't have other things going on, and you wanted to learn more, then feel free to start to explore like parallel, highly optimized designs. You want to avoid being in place where, you don't have anything working and you're trying to do something very clever at the last minute. So getting something basic, nice little state machine, perfectly wonderful way to do it. That philosophy will serve you well for the rest of this semester. So don't feel like you did a subpar job or anything. That this is absolutely what I wanted the team to do. So I'm content with that. All right, we're doing pretty good for time. Let's move on to group number 6.
Hello, can you guys hear me?
I can hear you.
Oh, all right. So we're group 6. We took a lot of the same. Our goal, I guess, was to it was a little different from what I've seen in other groups. So rather than like we knew that this project was going to be pretty short compared to our other ones. And so we used this time to work a little bit more independently than we would in other labs, trying to come up with our own implementations, just so that we can get more familiar with Vivado and with to get back up to speed with VHDL and everything. So, so you guys want to talk about?
Yeah,
the-
so here are the divisions of labor. So me, Sam, and Raphael, we really started on just a first working prototype, and Micah tried to think of ways that we would be able to speed it up a little bit more, and the way he thought about doing that is on the next slide. So we use this square matrix multiply unit. He wants to talk about that.
Yeah. So, when so I was thinking, and a lot of you have thought of this too, but to have a way to multiply vectors with the matrix in parallel would reduce the the total amount of like execution time. And so I ended up making a configurable square matrix multiplier unit that will that'll take a square matrix and multiply it by a vector, and my thought was that if you could reconfigure it, so you could change some of the specs like the like the amount of the number of elements inside the vector and the number of bits for each element, that maybe we could reduce the amount of time that we need to implement future matrix vector operations. And so that's what I did mostly, was work on this square matrix multiplier unit, and then once that worked, then we started making a the user logic. We started implementing user logic. Next slide. Oh yes, this is so this is the explanation. Kind of that goes into more detail about the square matrix multiplier unit. There's so all it does is it takes all the partial products. Every element in the matrix is multiplied by an element in the vector, and then that's all stored in the register. And then we used a process statement to add all of the results.
And then one problem that we ended up having was the DMEM was being turned into like flip-flops on the FPGA. So we had to, I think, yeah, as you can see there, it's kind of taking up all those leaf cells in the SMMU or nets. Yeah. So we had to move it off into like memory. I think you could set it like you can unset it in synthesis or something like that, which is what we did to remove it from the FPGA directly. And then, you know, some other problems we had, we spent a lot of time realizing that a signal is being driven by multiple sources from two different files that we didn't recognize. So this SMMU was really, yeah, so setting out of context for synthesis. So that's what that did. So this SMMU, the main goal of it was to have a component that we'd be able to just scale up and down as we want. So we are able to get 4 of these working correctly. We tried to increase the amount, but then we ran into problems with the hardware limitations of the FPGA, which made things a little bit more complicated. But we ended up getting 4 working, which decreased our time by a factor of 4. Any questions?
Any questions for this team? So do you recall 730 compatible sites? Do you recall what it was talking about?
It was talking about the FIFO somethings or
Like
another.
the block rams or the
Yeah, so-
FIFOs?
Yeah.
Yeah, those
There were-
were
Oh, I
Uh,
actually have it. The RAM 36 FIFO and the RAM 36E1.
Yeah, those are the block rams. Yeah, and I've been using that term, but not really defining it. So those are those hard-coded designs. So that's a lot of block rams that you'd be instantiating in that
Yeah.
version of the design. So the
Yeah,
fact that it has 730 is a ton, also, to be honest. But the fact that your design, as you start to do, not necessarily in this class, but if you were ever to do, building custom accelerators and using FPGAs, understanding where to put memory, when to buffer things. I mean, that's always a fundamental design decision. So I'm glad you got that experience.
Yeah,
doing
so
that
we
now.
also had to scale the amount of DMEM components we had with the amount of SMMUs that we had. So it also may have been like a lack of memory or something with that. We were thinking like maybe the FPGA didn't have enough memory to store all the DMEMs that it needed for the SMMUs. So
So
Yeah,
this trick
it-
would have been good to share. It depends on when you found out. So if you just found out recently, that's fine. It doesn't entirely make sense to me. I don't know everything, but it doesn't entirely make sense to me why that would lead to block rams, whereas when it just tries to synthesize the whole thing, it gives up. I mean, I feel like that's a bug in Vivado personally, but that's good to know, because that if everyone had known that earlier, we would have saved some collective hours of synthesis across the entire class, I'm guessing.
yeah, I think Micah figured that out, but I don't know when exactly he
yeah,
figured that out.
that took a few hours at least.
So out of
Um,
context is the Vivado term for, just do separately. And later, starting in MP-1, we do all the synthesis out of context. Kind of that's what it does by default. So it does every core that you have in the design separately, and then it has a final synthesis stage where it merges it all together. And that's wonderful in a more complicated design. So I have, 60 cores in the design, and I'm really only changing one at any given time. And you don't want to have to go through synthesizing all 60 each time. You're just doing that one, and that does speed it up quite a bit. Why
Yeah.
that leads to fundamentally different results is not clear to me for block RAM specifically, but I'm glad you were able to get it working.
Yeah, our synthesis, like we were synthesizing late last night. We are just trying different structures and stuff and seeing how many SMMUs we could fit. And our synthesis was taking like 5 to 10 minutes, but which was very nice compared to like the 2 hours that I was kind of expecting that it would take.
Well, that's good. Thanks, team. Group
uh,
7.
is-
Was there a question?
Sorry. Yeah, is there? Do we have just a little bit more time? There are a couple of questions that I was hoping to answer
Sure.
in the chat.
Absolutely.
So there's a question: what kind of performance was the optimized design getting? It wasn't great. We didn't realize that until it was too late. So we realized that we couldn't get very good results because, mostly because we had designed the square matrix multiply unit and our user logic to be really configurable. We had parameters for we had we were just learning about parameters and like process statements and stuff. And so we had parameters for like the size of the SMMU, the number of SMMUs in our unit, and we couldn't come up with a way to to pipeline the accumulation process. And that was really what held down the number of units that we could include in our design. But as Braden mentioned in the chat, there are ways to do that, and those are things that we will definitely be looking for and trying to do. So thank you, Braden. The other one is, did you happen to check the power consumption between your designs? We did not, or I didn't at least. Did any of you guys do it?
No, I didn't save the power consumption. I'm on a different branch, so I'd have to look at that, but I did not.
Okay.
I think it's just a button you press in Vivado,
Yeah,
and it's
yeah.
basically it's more of like an Excel spreadsheet model of what's happening, which is how we do a lot of dynamic power modeling anyway. So it's based on the instantiated components in the design and some arbitrary switching frequency assumptions. Here's what the power consumption would be. So I don't know how much I trust it, but I know a couple groups were interested in, yeah, how can we build lower power, more power efficient designs? I don't personally trust the FPGA tools well enough to know for certain that relative rankings of results of power efficiency actually mean anything. The actual time we can actually measure at least and say, yes, this took fewer nanoseconds than this other design. Power is a little bit more fuzzy with how if we're modeling it versus measuring it with that equipment. Okay, thank you, Group 6. Congrats. Group 7, you're up.
All right. Hey, we're Group 7. We've got some fun stories to share, but first we're going to give you a nice high-level overview of what we've done. So basically what we did is we created a pipelined multiply accumulate unit. So basically our matrix multiplication was being done in a very small granular format that we'll get to and talk about. And then basically our entire problem, once we had that done, kind of bubbled down into a memory offset, keeping everything filled operation. And then of course we were done once we reached a target value. So we're gonna talk about the top level design now.
Yeah, so this is our overview of our schematic. On the left side, that red block is our finite state machine. And we basically just had two states. The first state was kind of load A and grab the initial X value. Since the DMEM took one cycle to actually get values out, we just kind of had to delay all of our pipeline by one cycle. And then after that is just the operate state. Yeah, so we had the DMEM that he's got his mouse over right now. We were just like constantly, we never loaded A into registers. We just had a DMEM block always hard-coded to grabbing those A values. And then inside of this blue box is our matrix multiply unit. Nolan's going to talk about that more on the next slide. And then we had our counter that's just counting till we reach 10,000.
All right. Yeah, so this was the beef of our actual multiplication. So this is an older diagram, but you can see on the left are the 4 A inputs. So A 0, 1, 2, and 3. And then along the top are 4 X registers. So within each one of these max is it multiplies the two registers that are coming in through the top, or the two register values. So like A00 and X00. And so then it'll add it to the previous result, which starts off as 0. Yep. And so then within each one of those is a register too. So basically both feed in, multiply, and add, and then are stored. So at any given time, we're actually analyzing 4 values of X with one value of X being in each column. And then the output is just basically whatever the final value of X was. Or the final multiplication for each row. So out Y0, Y1, 2, and 3.
So this is our rough division of work. I started with the Mac designs and then worked on integration, and we edited our DMEM to be wider, have wider outputs. So for the A register, there was 4 outputs, or sorry, 2 outputs, and they were wide enough to each have 2 rows of the A matrix. And then for our X, we had we reconfigured our dmem.data file to have a full X value on one line. And then we had just one output for the dmem.
Yeah, and then I also did a whole bunch of the finite state machine stuff, and then I ended up being our Vivado pilot for a lot of this.
I ended up doing, again, the major implementation and integration of that big 4x4 set of Macs, and then working on a lot of the parallelization stuff.
I worked on the counter a bit, debugged, and ran Vivado a little bit as a pilot.
Yeah. So now it's time to get into some of the fun challenges we faced. The first one that we ran into was actually the first weekend on the project. I hopped on to the Linux machine and ended up killing the board through not actually logging into Vivado, just some issues that I had with my connection. And so that ended up putting both the board and the R bot to sleep for the entire weekend. To solve that, we were graciously offered the use of another team's board when they weren't on it.
And I want to add that that's probably something, just the reality of our situation, that's probably going to happen this semester. So every time something breaks really badly, the bot improves its functionality. So now we could have fixed that remotely now if it had happened again. But don't be surprised if I occasionally ping a team and say, hey, it doesn't look like you're too busy right now. Can team 3 use your board or something like that? Because it's just not all that stable what we're trying to do here. So don't feel bad about that. You didn't do anything wrong. Neither did the other group that had a similar issue this week. It just happens.
So the last group also touched on this, where they had a similar issue, where if you look on the left side, you can see that not only, our counter has about 76,276 connections total, which isn't right. If you take a look at the right side, you might notice that that's less of a design and more of a green brick. So we solved this issue. Strangely enough, it was a simple enable system on the counter that we didn't actually use. So we removed the tie to the enable, and it just worked afterwards.
Something else is probably happening because it wasn't an actual counter that was using all those cells, right?
I hope not.
This is probably using, well, that's the name of your label somewhere in your design, right? For a component or a process statement or something like that. And then that would have included the block RAM, I would imagine, the DMEM, I would think. Inside that, and then I don't know about the enable signal, but I can't be a counter, I would think, itself.
Actually, this component didn't include daemon. It was outside of this.
Maybe it got folded maybe it got merged in or something though, because right, we know what a counter looks like. You couldn't build a counter with 76,000 nets in it, right? What would those nets even be doing? So anyway, a lot of people saw green blobs this week.
All right, and then one other kind of miniature challenge we had was that we were basically thinking about the timing of this whole thing wrong. We were taking into account done signals after they were done, and so we spent like a week trying to figure out why we were getting all zeros, and it was just because we were setting done a cycle too late because we were trying to set those pipeline registers on the outside rather than the ones on the inside. So that was a fun little problem.
Should have seen it in simulation at least though, right?
Yeah.
Okay.
Yeah.
We had an issue as well where it was around 7 o'clock last night. We went in to check on the TA and see if there was anything we could fix. And we found out that we were doing our math wrong about the entire time, where essentially we were supposed to be, what we thought was we were doing the original matrix sum, where we had to generate 10,000 different y vectors from the 10,000 x vectors and multiply by x, and didn't realize we were supposed to be accumulating y0 every cycle. And we found that out at 7 o'clock last night, so we spent quite a few hours trying to fix that.
Okay, yeah, so here we obviously had a very late start to getting our design finished up, but we did get something to run. It doesn't run crazy fast. We didn't have time to really try and optimize anything once we reworked our design to actually fit the problem. But you can see from our utilization chart, have a lot of space. We could have scaled this up, parallelized our multiplication portion significantly. With our doing the wrong problem over in this bottom right corner, we did scale up that parallelization, and we were using about 33% of the hardware, and we were running 10,000 calculations in a pretty good time there, just not actually summing them all together. So we felt good until we realized we were doing the wrong problem.
Thanks, team. Well, I'm glad Steve was there and available to check that, because looking at your diagram, it looked close. It just, I guess you would have needed to have a feedback loop for the accumulation, or because it wasn't clear why you'd have to start entirely over. I'm not going to press you on it if you don't know it off the top of your head, but if we go back to this diagram,
we definitely
pretty
reused
close.
a lot of stuff for sure. We were able to keep our whole matrix multiplier kind of pipeline there. We just added, if you go back one more, I think that diagram is updated more so. So we added the summing elements on the backside. We were trying to drop this whole thing into a generate statement, or basically this whole thing. And we were having issues just in VHDL getting our summing across the end of the generate statements. So
so once you want to parallelize all this, then it becomes pretty messy, because then you're having to accumulate across all those different blocks. That becomes a little messy.
And we couldn't get through the compiling errors with that synthesis in time. But
any questions for group 7? We're doing pretty well for time here today. We're right on schedule. And I would just say some late night struggles. So I'm really glad Steve was able to help out. So thank you, Steve, and everyone should thank Steve if they ever see him on campus. I really like what the team did. I mean, don't be embarrassed. I say this. I just like the diagrams. I like the breakdown of the problem. I like the breakdown of the team and how you were dividing things up. It just seemed, even though I guess it was wrong up until the very last minute, it just seemed really great. I just like the whole approach that you took, and it just that approach will pay dividends, as we go into MP1 and later. So I thought it was really great. Even with the board murder.
Yeah, we will work on reading the lab document in future labs.
Yes, especially if I highlight something, that means I'm looking for exactly that, and I'm already going to see some people who are going to lose some MP0 points when you shouldn't have lost any, but it's not a big deal in this class, so no one should stress about it. All right, group 8, you are up.
Hi, we're group 8. So Aaron was our driver. He helped, he pretty much drove Vivado. He wrote the multiply accumulate logic and helped with bug fixing. Josh is our navigator. He worked on the read logic, also a lot of bug fixing. I'm Ahmad, and I was also a navigator. I helped with some of that too, but mostly about the write-up and making the infrastructure work, which, as you'll see later, was a kind of a big issue.
So is navigator and driver, is that a 288 terminology that you've
kind of like,
okay,
like Aaron was more so on like Vivado. We were just watching through Discord trying to help him.
It seems like backseat driver. I don't know, right? Okay. So multiple navigators for one driver. That's fine. I mean, use that if that works. Whatever works for the team is perfectly fine by me. Yep. MP1, you can have real titles, I think, with enough of the tasks we have to do in MP1. You don't have to worry about who's driving or who's.
Yep. Next slide, please.
I think back one. All right, so we're gonna start with the first question. What is the
Yeah, so this is sort of just a 5,000-foot view of our design. Just our five-state machine, similar to what other groups had. The main driving loop in that is S1, S3, S4, where we load the X vector, we calculate it, and then we add it to the accumulate. S2 is just a one-time thing where we just load in the A matrix. That's our basic state machine, and then the bottom thing is just the simple multiply and accumulate, which I think every group had. And I suppose we never actually put our results up on slides. We never actually got the right results. We had the right order of magnitude, but we never had the exact answer. And our time was around, I think it was 4123A in hex.
I actually have, I can just throw it in here right now. Like, yeah, it's like 4123A nanoseconds, but this is, we had the same mistake as the other group before us, where we thought we didn't have to accumulate, we had to generate 10,000 Y vectors. So this result is using the 10,000 Y vectors. Some other issues we ran into were we kind of forgot that X on the waveform means the signal is being driven multiple times. And once we figured that out, like we stopped chasing like all of our phantom bugs and we fixed that. But then we ran into some really weird issues with the hardware server where at first like I would run it and we would get this weird error like reset failed for dev unknown. We checked the status of the hardware server, it would say it was defunct. We had to call in Zambrino and we walked him through what was happening, and it just
Yeah, it's still
turns out our
broken.
board just
So
yeah.
Xilinx 8 is still broken. So everyone, we will multiplex, time multiplex the other 7 servers. We should figure out what's happening. So it's not a software issue. Something, I'm guessing a cable or something got loose, or I don't know. I can't get to Durham to even check it out myself. But we'll get that figured out, and in time for you to do just fine at MP1.
Okay.
No, that issue with well, first off, there's a couple of things that I think every team should be taking away. Is that simulation is pretty important, right? You can get a simulation run done in 2 or 3 minutes, right? Certainly, if you have a nice scriptable simulation that you don't have to manually force and add all the signals and do all the million clicks. If you have a nice little tickle or script or a test bench, 2 minutes you can simulate and see how your design's looking. And for a lot of the stuff we're doing in this class, it's not even really necessarily even worth it to try it on the board until you have some confidence in your simulation, just because of the asymmetry and how long it takes to do a board test versus a simulation test. And definitely for MP1, you should have some confidence that what you're doing, doesn't have floating signals or multiple drivers before you even worry about hitting implementation or generate bit stream. And then that's the other thing. When you get a final result that's wrong, that's tough. I mean, that's rough. I mean, it's better than getting all floating values or nothing coming out, which will be a common occurrence, in later labs. But getting a wrong value back out, it's definitely, when you go into your next simulation, it's how can I simplify, or running on the board, how can I simplify the data I want to send to this design so I can do it in pencil and paper and know that I have the right order of magnitude, or it's an off by 1 error, or because those are going to be pretty hard to test otherwise. It's never going to be the case where everything's fine, but the triangle is off by 10 pixels. It'll never be something as simple as that. It'll look like garbage. So how do I get a design in there that I can actually trace through and see where things went wrong? You'll start that. Hopefully for MP1, you'll be seeing that, as you go in. And simulation is the way to do it. Can I take my OpenGL code, convert that to an equivalent kind of simulation input, and check that my mathematical understanding is correct, my logical understanding is correct, and then my HDL is correct. And then we kind of cross our fingers and hope that the tools generate the right hardware for us from what we believe is simulating correctly. Other questions for this team? Otherwise, we will jump back into group 1. We'll start at the beginning here. All right, you guys are doing great. Let's keep it up. You're up, group number 1.
Okay, cool. Yeah, do we need the next slide? So yeah, we're group 1. Braden was in charge of Mac unit and the Mac test bench, as well as debugging and doing pipeline attempts. I was helping out with the Mac unit, and I made the control unit test bench, and I was helping with general debugging all throughout. Matt was the diagram master. He took the charge of the diagram, and he assembled everything in user logic once we had all the units all developed and tested. And he helped debug user logic to get it in its working state. Same with Braden, myself, and Nathan, who made the control unit himself.
So here's our overall diagram.
You know, hold on. I at least can't hear you all that well. Maybe it's just me, but this new voice that has come in is very quiet.
Hold on, let me plug in some headphones.
Like you're on a submarine.
Now,
Yes.
how about that?
Yes.
So yeah, so here's our overall diagram. It might be a little bit hard to see, but we kind of took originally we were kind of thinking the 381 approach of just, all right, we got to build everything from the ground up, right? And so if you look down at the bottom, there's some reminiscence of like an adder down there for, comparing values and whatnot and looking at overflow bits and demuxers and whatnot. But overall, this was kind of what our design ended up being. We were hoping for this, a really simple design of just, we've got our DMEM pulling out. Each one of those Mac units is just going to be running a line of the multiplication, and then we're just spitting out our outputs, eventually once we put our done signal high. We ended up having a few issues, one of which being that, we thought it would be easier to just not pipeline anything, but in reality, that ended up being kind of tricky because we ended up hitting a lot of timing issues and whatnot just with, and it looked like that was a common thing with a lot of groups too, is just, we were realizing, okay, yeah, when you have this much combinatorial logic and you're doing adders, even with, DSPs and whatnot for your multiplication, that you're still going to probably run into a lot of timing errors just, even after all your optimizations. That was one thing that we definitely had to take into account, going forward.
Yeah, so kind of the biggest challenges and issues that I think we really had was we lacked any sort of real planning, which I think kind of hurt us. We actually ended up essentially redesigning many aspects of our design from the ground up, like repeatedly. And every time we redesigned one component, that would have impacts on all the rest. So it ended up just being this whole mess of kind of redesign work as we kind of stumbled over issues, primarily with latency and then eventually with accuracy. As Matt alluded to, we first kind of had issues with latency, and we tried to address it using DSP, specialized hardware, and that ended up just kind of complicating things a lot. And we eventually determined it would just be much easier just to proceed with pipelining. So our ultimate Mac at the end of the day was actually a very simple design. It was a 3-stage pipeline where it would read in your inputs in the first stage, do the multiply in the second, and then do all of the additions in the final stage. Using that approach, we had about 3 nanoseconds of slack, so we actually had a good amount of room where we could have improved. We probably could have upped our clock 30% had we the time. But nevertheless, it was at least met our timing constraints and seemed to give us an accurate answer.
And I would just add, and I've mentioned that to a couple teams, that it's kind of hard to say necessarily with regards to the slack, what that means. So the tools try as hard as they need to. When they meet timing, they give up because they've placed and routed the design and they've met timing. You may have had quite a bit more slack as you continued to try. If you were to crank up the clock frequency, it may have continued to succeed even with more than that 30%. Likewise, for groups who are failing timing, there's a point at which the tools just give up and say, wow, this isn't going to happen. Why even try? We've all done that, right, in our life. So so if you're missing timing by 50%, that doesn't necessarily mean the situation is as dire as the tools say. So success you can take and work with. Failure doesn't mean you're off by the amount you failed by. We're not doing a lot of dynamic clock changing this semester. It's enough to do with just a solid 100 megahertz clock throughout. Another thing I wanted to add is I really like the diagram. So Matt, you're the diagram master, I think they said, and I really like this diagram. Something I mentioned last Wednesday in lab, and I want to make sure that everyone kind of gets that point, is structure in your design is a wonderful thing. So I think this is wonderful. Now we could quibble. Do you need to know every pin at the level of experience you all have now? Do you need to know every pin in your diagram? I think sure. If you have the time to do it, this is just wonderful. If you have to keep changing the design, it becomes a pain, right? As you have to keep modifying this, but it's a wonderful design for a diagram for your design. That doesn't imply that you have to follow an equally structural VHDL coding style. So you have structure in your design, you have different things, and you have data flowing between them, and you have control. That doesn't mean your VHDL has to be equally structural, and you have to have a compare component and a separate component for an inverter and things like that. You don't have to have that at all. So that can still be data flow or behavioral. But having this picture in mind of what the system is supposed to look like, that's always helpful, no matter how you're doing the coding. And so I think that's great from that perspective. All right, we have 2 more groups, and we're doing okay with time. So group 2, you are up.
All right. Hey, this is Daniel speaking. I'm on group 2 with Ryan, Maggie, and Christian. I'll talk about the division of labor. So for this project, this lab, we didn't really define roles at the beginning per se, but this is just kind of how things ended up going. We kind of took this 288 approach where we had these 2 drivers and 2 navigators. And so for our very early initial design, we had Christian and Maggie get started on that really early. And then when we came back together, we ended up modifying our initial design, and we had Christian and Ryan kind of driving that implementation. And then once we got that initial implementation working, I branched off and worked on the report mostly. And then Christian and Maggie actually stayed after and tried to get a design or worked on design improvements at the last minute. And then Christian and Maggie will talk about the architecture.
So the FSM that we created has 6 different stages. The first one, S0, is just for initializing the counters and the addresses. And then for S1, we allow the VRAM to latch previous addresses, and we have a count for that so that it does all of them. We then go to S2 where we load our values into the A matrix, and we also count that so you get all the rows that have their values. And then once the count is 3, we go to S3 where we perform our MAC calculations. Christian's going to talk more on how we implemented a pipeline design in that stage. And then once we get to a count of less than 10,000, we go and we set our SDone to true, which we have a 2 count for. And then once that's done, we reset SDone to false.
Great. So the diagram, top right, that's being pointed to right now is a very rushed diagram of our pipelining. We really got this done probably at around 11:45 last night is when we were actually synthesizing things correctly and getting correct results. So it's very rushed. But the general idea is that our first stage simply pulls from our single block of VRAM. And we have SA matrix loaded up in what would eventually be synthesized into just registers that permanently hold that value from our previous state. And we just run our 16 multiplies that we would need as we unrolled that matrix multiplication loop twice. So essentially, we're just iterating through the 10,000 X vectors that we need to go through. Those 16 multiplications that we perform all get sent to our single multiply pipeline register, which is then outputted, and we do the 4 accumulates with also the backtracing for our Y out for the respective Y0 through Y3. And the reason for this, that we primarily implemented this, is that our previous design was functioning, but we weren't quite meeting timing. We had a pretty bad worst negative slack, as Ryan will explain later. And this design helped us mitigate that and actually pass timing. And I should also note that this finite state machine is just a modified version of the process 2 that was given to us in user logic. So that's just kind of where it fits in. So Ryan will explain some of the challenges we had.
All right, so challenges and bugs. The first real challenge we hit was that we had 6+ hours. We basically wasted on Saturday, I believe it was, just on synthesis alone, and that was on Christian's personal machine with a pretty good processor and 24 gigs of RAM. And we ended up solving this by switching from DRAM to BRAM. The way I kind of understand it, and correct me if I'm wrong, is when we were using DRAM, it was trying to physically build the DRAM on the actual FPGA chip alone, or itself. Instead of when we use the BRAM, it was using pre-dedicated memory that we're just writing values to. And then following that, hardware timing dependencies that weren't present on in software that basically caused our simulation to run indefinitely. So we would get to the end of our calculation and our board would just spit the ending values in the terminal PyCom. And I believe that's what is represented on the right in that like black box is just the repeating values. So essentially our S done signal, we were setting it for a clock cycle, and then we were setting it to false afterwards. And what I believe is what I believe was happening was basically there was a timing dependency where we were setting the signal high at the same exact time as we were trying to sample it. So for some reason it wasn't seeing it as high, and then we were setting it false before it was actually able to grab it on the next cycle. And so yeah, we just buffered a cycle basically to fix that. It appears that there's a different timing delay between port A and port B on the BRAM. I think, Christian, correct me if I'm wrong, but our worst negative slack before the pipeline design was like -200.
So that you're talking about our total negative slack. Our worst negative
Yeah.
slack is -2, almost -3.
Okay.
But all of our really poor critical, like all of our poor pathing at our critical path were exclusively from port B of BRAM.
Yeah, and we had taken a screenshot before, but I don't think it's in this presentation, that basically it showed two different issues. And if you could go back to the previous slide, yep. Potential issues with synthesis. Oh yeah. So the initial design that I I guess the secondary design, branching off of the sort of rough initial design that Maggie and Christian had first came up with, I tried to use variables in our process statement, but Christian let me know that I guess variables have an issue with synthesis on the actual board itself, because signals, you can't update a signal and then try to see what's on that, basically see the state of that signal like in an if statement in the same exact cycle. You have to wait a cycle for that signal to set, whereas variables, you can basically, set it, update it as many times as you want within that cycle without having an issue. So that kind of changed our design. And then there were a large number of steps in our pre-pipelined design when we were doing our Mac. Whatchamacallit? Oh yeah, Maggie and Christian yesterday basically used their quote unquote doubly big brains and realized that there are a large number of transistors we have to go through. In the previous slide, I believe it is, you see that when that sort of fuzzy block in step 3, we essentially, after we load in all of our A matrix, we basically every cycle load in 4 values for our X matrix, so X0 through 3, and then we multiply those together and then we add them all in the same exact cycle. And so that's a lot of basically things to do, which resulted in the -2 slack. And then another thing I want to make mention is that our DRAM design, after we got the 6 hours of synthesis, wasn't our worst negative slack like 2000 or something? Or
You're still thinking of total. Our
oh
worst
yeah,
negative
total.
was closer to -5.
Okay, yeah, my bad. Yeah, so that wasn't too good. But when we switched to BRAM, our synthesis time dropped from 6 hours to like 15 minutes approximately ish. So yeah.
So thanks, team. And I would mention that so the issue with the DMEM getting inferred as distributed RAM primitives, which it's using the lookup tables as a little 64-bit memory storage individually, and it has to distribute those throughout the chip. That was not my goal. So whether that was a Vivado bug, a me bug, or whatever, that teams who struggle with that was not my goal. But the issue of understanding that critical path in practice of how much math can I get done in one clock cycle was an intention, that you teams would see that and work around that. This is not a very high-end chip, I get. I mean, for the price I paid for it, it's not that expensive of a board. So I actually would have thought you could do, those multiplications followed by those chained additions in a single 10 nanosecond clock cycle. But on this board, this particular chip, we can't. So your designs going forward are going to have to keep that in mind as well. So I want every group to kind of remember that there's a certain amount of math my design has to do. Maybe one multiplication and one addition, sequentially, and then you can have them in parallel if need be, but one of them sequentially in a clock cycle is probably a good rough order estimate for what you can do for your 10 nanosecond clock.
But yeah, just quick overview of results. You see, our pipeline result was just ever so slightly slower. Ideally, as we were to do a larger matrix operation that would be offset. And our utilization is relatively low, so there's a lot of room for parallelization as well. So we could slice up our X matrix and go ahead and just do 2,500 iterations instead of 10,000 iterations by adding the appropriate number of multiplications to our pipeline. So there's further room to optimize. And yeah, I think there's just one more slide.
Okay.
But that's it. It's just a meme.
Work smarter, agreed. Well, I don't blame you. How would you have known that? So I didn't give you any hint that that's something you had to do for this design. But starting early, I think that's going to have to be the case for all of these. But you got it done. So there you go. Okay. Don't call it DMEM or DRAM because we think of off-chip DRAM when we're doing that. So distributed RAM versus block RAM. All right, last but not least, and we're going to be roughly on time here. I know if people have to leave at 11:40 or 10:45 on the nose, that's fine. We're seemingly doing okay otherwise. Group 3, why don't you get started?
Nathan, do you want to explain the diagram?
Yeah, if we go back to the first one, I need something a little bit better. I need a better diagram, please. Wait, where's the first diagram?
Did you not? Oh, okay. These are the diagrams we have. Nathan can just explain these.
Sure. So what they have presented here is our most recent version, which is kind of funny because it has our lowest quality sketch. Thank you to, I think, Reed, who redrew it. So this version is based on mathematical manipulation of the problem, where you say the summation of a times x, where a times x is a smaller operation, you summate that 1,000 times, can be done instead by the multiplication of a with the summation of all the x's. So that helped us achieve, first of all, higher clock rate and also just simpler hardware that was much easier to synthesize when we made it highly parallel. So you can see it's not perfectly drawn out how in excruciating detail, but what happens in the first stage is we read from memory in parallel because we have rather wide 2-port memory IP that we use from Vivado, where we can read 4096 bits per port on 2 different ports, which results in, let's see,
64 vectors.
64. No, actually, it's 128. Oh. It's 128 vectors of 4 16-bit integers per cycle. So every single X will be accumulated in registers, which means we actually have 512 registers to have our 4 by 128 registers of X, because there's 128 X full vectors that are registered every cycle and accumulated. After that, state machine runs, since that can run at a higher clock because that operation is rather simple. that data is glued to a second module, kind of similar to how we glued user and fixed logic in the original architecture, to what I call the flatten stage, which basically removes all your parallelization by flattening your 4 by 128 array of x's into just 1 by 4. So like an original X vector. So it results in a 48-bit accumulation of X across the entire D memory. And then after that, it runs into a dot product module, which is a pretty simple implementation, similar to what a lot of people did, which would, in one cycle, multiply and add them all up. But since this whole flatten and multiply stage happens only once in a one-shot run, that actually had no reason to pipeline this. And if we basically wait for the accumulation is done signal, and then the separate module just runs the combinational logic to add up and multiply all at once, and then it waits for its clock rate one cycle to say, hey, I'm ready too. And then that goes to fixed logic.
All right, so can everyone hear me?
Yep. Yes.
Okay, so just to discuss the division of labor real quick. So basically I want to say that Nathan sort of got the design initially started up and running, and then after that we were just like, all right, let's just optimize this as much as we possibly can. So then, you know, we had lots of group sessions. Basically Reed was kind of like the driver, and then the rest of us were navigators. You know, I want to say Justin and Nathan had a lot of the ideas that ended up like really optimizing the design a lot, and then I was just kind of there for, you know, moral support and all that. But you know, ultimately the pick you see is the most accurate. So
And can I mention that the first design he mentions was you'll see in the next slide, it was very similar to some of the other implementations where you'd read with the original DMEM version 4 integers per cycle. So we'd read as, you know, populate a single vector of X, multiply and add it all in one cycle. So it's a pretty simple architecture. We did not start with anything stupid, and we have several different versions of ours that were parallelized differently, and we tried to get them work and they couldn't work. So
yeah, so sorry.
You're fine. I'm done.
So yeah, lots of the issues initially we ran into with timing. So the solution to that, at least early on, was just to cut the clock rate by a quarter down to 25 megahertz just to get it to run at that speed. You can go to the next slide talking about some other issues. So initially we ran into the same like the original DMEM was like getting absorbed into I think our dot products or something. So the LUT count was skyrocketing, and it hung on the place design or route design stage of implementation. So initially I just switched to an implementation strategy that didn't do anything with timing. It was the flow quick one. It had the word quick in it. I was like, well, that's what I need. It needs to go quick. So ignoring timing to pass implementation is not a good idea, because then even if you have the right design in simulation, it doesn't output the right stuff. So that's when we underclocked it down to that 25 just to get a correct output no matter what speed it was at. And then to actually fix that, Zambrino suggested we switch over to the block memory IP core, which was great because that removed a ton of the original LUTs. I think it went down from like 36 or 45,000 down to like less than 1,000. So the block memory stuff was great. We were able to customize it a lot. So we thought, okay, we'll throw 4 in because, you know, the more that we can read from at once, the better. But then the LUT count got up to like 436,000, which was just absurd. It sat in implementation synthesis forever. So we went back down to 1 block memory and then just cranked the output up to 4096, which is what we ended up with, the 2 output at 4096 bits. And then one of the other implementations, since I really liked this block mem IP core, it was easy to throw in and configure and stuff. I looked for the multiply accumulate one, and on Vivado's IP core, listing page where you can sort, I checked, the FPGA we're using, and I made sure that Vivado was checked, not the other software, and it pulled it up, and I was like, this is great. But for whatever reason, Xilinx doesn't want to update their website, and the multiply accumulator that I was so excited to use and just throw in the design was deprecated and not actually supported in Vivado, even though their website suggested otherwise. So that was a little frustrating. And then Justin can talk a little bit about kind of how we moved on and how we maxed out or designed beyond that.
Yeah, so our design at that point was just trying to do way too much in a single cycle. We were doing the dot product of the vectors we were reading, which at the time I think was 32 vectors per cycle. And then after the dot product, we were trying to add them all up. But the way we were adding in Vivado was also not efficient at all, because the way we had it written out was in a loop statement, and it was doing all of the adds sequentially. So it was taking a really long time to not only synthesize, but also like the clock rate we could get, I think was only 50 megahertz at that point. And so one thing we did to kind of alleviate that was we kind of created an implicit pipeline by using the DSP slices, because they have like a multiply accumulate DSP like template already for you. So you're able just to basically import that into the project. And that allowed us to actually get the clock rate back up to the original 100 megahertz. But I think our timing after doing all of that was CBC, so just under the TA time. So we couldn't really figure out how to increase the clock rate beyond 100 megahertz. So of course we decided to just completely redesign the architecture. And so I think Nathan like had the idea like, oh, we can just add up all of the vectors into one just single vector, the 48-bit vector. I was like, you know what? I think that might actually just work. And so then we decided to also separate out the flattening of it and explicitly tell Vivado how to do those additions so they weren't going to be sequential. And so what we ended up doing is actually clocking the two components. Like I think we eventually got it up to 200 megahertz on the actual accumulation and then 50 megahertz on the flattening. Is that right, Nathan?
Yep. And I was quite surprised we couldn't hit faster than 200 on the accumulator, because I was thinking this would just synthesize down to a DSP, some sort of something like it's just one add and one register. But at some point, he kept running into these like interesting timing issues, and I think maybe some of them would have been alleviated if I had used some more proper glue between the two modules. Zambrino recommended a FIFO, which I did not quite do. I did something with like essentially a register and then just one cycle delay, and just because I didn't want to have to figure out how to grab the right kind of IP again from Vivado. But I think maybe we would have been able to fix some of the timing issues at the higher frequencies, if that were the case, because we were able to hit the 50 megahertz. Megahertz is kind of a funny way to describe it. It's more of just the period. What's the period of 50 megahertz? 20 nanoseconds. So like a 20 nanosecond period, critical path was totally achievable for the entire flattening and multiplication stage, which was interesting to me that we couldn't go any higher than 200 on a single addition. But yeah, our current fastest time is, that's what we hit with 100 megahertz fixed logic, 200 megahertz accumulation stage, and 50 megahertz add it all up and multiply it.
And I appreciate all the memes that everyone added here. I kind of get that one. Not that some of them I get, some of them I don't get. You don't have to explain them to me. That's perfectly fine. This is a pretty fun design. This approach of kind of reinterpreting the math, within reason in a class like this is completely valid. Yes, in theory, someone could have said, well, I just know what the result is, so I'm just going to put that in a memory and call it good. And so I had to add some verbiage regarding, no computation of the values. But you didn't do that. You computed all the values. You just recognized that there's some distributive property of the multiplication and the adding that you can then reverse the order of them and get, as we kind of were getting at in that one in-class exercise, you can kind of reverse the order of the loops and effectively get faster performance on that part. And that part I didn't think of myself. So the reason I would say you beat the ETA's time is the fact, realizing that not having a single frequency goal for the entire user logic hadn't occurred to me, or I didn't put the effort in, but realizing that some part of it could really be overclocked, other parts you can actually then downclock, and because they're not equal in terms of how much you have to use those components, you're able to get a pretty good time back out. So that is pretty impressive if you think about it. If you think about the power of hardware, right? Even this budget FPGA board we have here, how fast you're able to get that multiply matrix vector or multiply accumulate operation happening on those 10,000 vectors. That's a pretty cool result. So I told this to your group. I'm going to tell this to every group. And as we wrap up here, this design doesn't really go forward. So hopefully the skills go forward. So what you learned about Vivado, remembering some of your VHDL days, synthesizing, simulating, all those kind of things, all that's very relevant for us. But we kind of start over again. So MP1, I do want every team to make sure that you look at that, read through that assignment before Wednesday, do that pre-lab before Wednesday. So you come in and ready to go. There's a bit more infrastructure to learn, but it sounds like nothing that the teams can't handle based on your progress in MP-0. I'm really enthused by what I saw. This was just tremendous. I think the teams just did wonderful work. I said on day one, I want every team, every student to get an A in this class. We're well on that. We're well on that trajectory. So just keep it up and know that I have some challenges, ahead of you for MP1 certainly and going forward. But it's nothing. I think the teams, if you work together and if you support each other as a class as well, I think it's nothing you're not going to be able to overcome. In the interest of time, I'm going to shut things off here. Anyone who wants to chat otherwise, I do have my office hours in about 5 minutes here. Looking forward to it and looking forward to seeing what people can come up with for their creativity for MP1. Otherwise, let's leave it here for today, and we'll pick up where we left off on Thursday, certainly.